Up until now, we've been talking about simple harmonic motion, which doesn't include any sort of drag force. There cannot be friction, there cannot be air resistance. So now we're going to talk about what happens when you do add some sort of drag force. And in this case, we're going to assume a model where our drag force is proportional to the velocity. And in particular, notice here that these are vectors. So the drag force is opposing the velocity vector. It points in the opposite direction, but it's also proportional to velocity. So opposite direction depends on speed and some constant b. So this is a fixed value. And so what's going to happen in this case, we're going back to the simple situation of our mass on a horizontal spring, is that we have our spring force, where again we've defined x equals 0 to be our equilibrium position. But now we have a second force, which is going to be from our drag. And this now is going to give us mass times acceleration. So, as we've been doing up till now, we want to get this into a differential equation form to make sure that we know how to solve it. And it's going to look like this, that I divide out m, I divide out m on every side, so I need to have b over m here. And note that now I have x, I have dx, which is coming from my velocity, and then I have the second derivative. Does this look like something we know how to solve? Well, maybe we just need to rearrange a little more. So let's try moving these terms over. And again, this needs to be b over m. And I still have 3 terms. This definitely doesn't look any better. I've shoved this all together, and again, we see that we have 2 different derivatives. So this is not a differential equation that you know how to solve. Now, the caveat being, perhaps you've already taken Math 309 and you look at this and you say, oh, I totally know how to solve that. Otherwise, you would have to say, refer to a textbook or ask someone. Now, you look at this differential equation, if you haven't had DiffEq, and you decide to ask your physics professor, Dr. Ackerman, what solves this? And what she says is this solves it. You have x, where again that's our function of time. You have some normal constant out front. You have your phase constant as before. You have cosine of omega t looking great. And now there's this exponential term hanging out in front that includes b and m and is a function of time itself. This isn't a constant. This also depends on time. So this is quite different. Now what you can do is this could be considered a guess and check situation. Now I don't know why this would be your first guess, but you can actually take this, and if you take its first derivative, and if you take its second derivative, and if you plug it back in, you can check that this is true. Now the caveat here is I haven't told you what omega is yet. And so by taking the first derivative and the second derivative and plugging that in, you can actually see what omega must be equal to in order for this to be the solution. And the answer is that now omega is the square root of k over m, which is what we used to have, but minus b squared over 4m squared. Oh, right. So now there's this second component of omega that's actually shifting it from what it would be if it was undamped. So one of the ways that this gets written is that we can say omega naught squared minus this correction term. Now omega naught here is not the initial angular frequency, it's simply the undamped angular frequency. So if b was 0, if there was no damping, what would it be? So this is kind of like saying you take your mass on a spring, you measure the angular frequency in vacuum, and then you turn on air resistance and you see how much it changes. So this would be your correction term. So this is a little more complicated. So if you were to solve this in all cases, this is challenging to understand. So what we're going to focus on is what's called lightly damped. This is general for all situations, but now we're going to go to the situation where it is lightly damped, meaning we have a small damping force. Now in physics, we normally have a mathematical condition that we use to define whether something is large or small. We want to compare it to something else. What we're going to be comparing this to is that b over 2m, how it compares to omega naught. And remember that omega naught was square root of k over m. So as long as b over 2m is small compared to this, then omega is approximately equal to omega naught. And that's really just saying compare these two terms And as long as this second term is really small, then we can ignore it. And omega is approximately equal to omega naught squared square rooted, which is just then omega is equal to k over m. So that isn't quite an the approximation is here, but you can only do that approximation if b over 2m is much, much smaller than the square root of k over m. So again, this is an approximation that is only true in certain situations. Now, if that's true, what happens is that you have these oscillations that are gradually decreasing in time. And we can think about this as just saying that our amplitude is changing with time, where that's given by that exponential term times a, and then we're left with cosine of omega t, where we don't have to worry about that really complicated form of omega. We're just going to really use square root of k over m. So in this case, there's then two pieces to think about. That our maximum value of x, or our amplitude, is decreasing with time with this exponential function, but then we have a standard oscillation inside of it. We refer to this exponential decrease in amplitude as the envelope. And the envelope, again, is going to have this exponential form, and note that it's negative. So that means it starts at a maximum value. If you plug in t equals 0, this exponential term is 1. So it starts at some maximum amplitude and decreases with time. If b is equal to 0, this is the same as having no damping. So a stays constant. And what we're going to talk about next is that means energy is conserved. That's our normal situation. As we increase b, you have more and more damping, and your a decreases faster. So larger b means amplitude decreases faster, but the shape that it decreases at is always going to be exponential. So if you then have this exponential decay in amplitude, that actually means your energy is decreasing with time. Remember that originally we said that all of your energy is potential energy at the maximum position, because there your kinetic energy is 0. So we can say that energy is a function of time as long as we're just thinking about points where it stopped because it's at maximum position, is 1/2 k times our x squared, maximum. Well, our maximum value of x is this thing that's exponentially decaying. So that actually shows us that our energy is exponentially decreasing with time. Now in physics, we frequently put any equation like this into the same form, where we create what we call a time constant. And depending on how you want to talk about this is kind of a little messed up here. We could call this 2m and then have it like this, or you could keep the 2 in the exponent, but I would say it would be better to just put the 2 here. So our time constant is 2m over b, and then we see that we just have an exponential decay. And the reason we would do it this way is then you always talk about how long it takes in terms of time constants. So the same mathematical relationship comes up if you're talking about, for instance, radioactive decay. We have the idea of half-life, and I know that in chemistry there are similar processes as well. In biology there are processes, some of them exponentially increase, but you also have exponentially decreasing. So honestly, in the chapter, damped oscillations is not the most important topic, but part of why I wanted to go into this here was to show you that this sort of behavior is going to be something that you've seen in other classes and frequently is coming from the same type of differential equation if you have an oscillating behavior as well.